Right now, somewhere in your house, a furnace is burning fuel through the night to keep you warm. And the physics says most of that heat is gone before it ever reaches your body. Most people think the answer to a cold home is a bigger furnace, better insulation, or a smarter thermostat. But the truth is, every modern heating system is built around a fundamental physics mistake that Scandinavian farmers solved 800 years ago for under $40. And the worst part, the heating industry buried that solution the moment electrification became profitable. We're covering the specific heat capacity numbers that explain why masonry stores heat 100 times better than steel. The exact burn protocol that charges what's called a thermal battery for 18 hours, and why radiant heat from a ceramic wall makes you feel warmer at a lower air temperature than any forced air system can. The Kakel-Yugen, a masonry tile stove built across Scandinavia, Finland, and Russia since the 12th century, was standard in northern European farmhouses through temperatures of 20 degrees D, C, or 4 degrees F until utility electrification campaigns in the 1960s replaced it. Not because it failed, but because it generated zero recurring revenue for anyone. The conductivity trap is the first issue. Your steel radiator isn't a heater, it's a heat discharger. Every steel baseboard heater, every cast iron radiator, every sheet metal furnace casing in your home shares the same fundamental physics problem, and that problem is thermal conductivity. Steel has a thermal conductivity coefficient of 50 W per meter per Kelvin. Masonry and ceramics sit between 0.5 and 1.0. That means steel moves heat 50 to 100 times faster than masonry does. Now, that sounds like steel should be better, and that's exactly what the heating industry wants you to believe. But moving heat fast isn't the same as storing heat. Your steel baseboard heater reaches peak surface temperature in a few minutes, and the moment your furnace cycles off, that surface drops back to room temperature within 15 minutes. It physically can't hold thermal energy. The specific heat capacity of steel is 0.5 thousand joules per kilogram per Kelvin. Clay and masonry sit at 0.9. So, steel holds less heat per kilogram and dumps it faster. That combination is the conductivity trap. Your furnace runs a heat burst every 15 to 20 minutes all night long, burning fuel continuously just to compensate for the heat that steel can't store. That isn't a design failure, it's the design itself. Continuous fuel burn means continuous revenue. The conductivity trap is why your heating bill is recurring. A material that can't hold heat requires a fuel source that never stops. So, now you understand why the conductivity trap makes every steel heater permanently dependent on fuel. But that's actually the second biggest problem with modern heating. The first is what all that steel is replacing, something masonry can do that no metal on Earth ever will. That's called the thermal battery, and the numbers sound impossible until you run the physics yourself. And this is the core physics that makes everything else in this video work. You've been paying for a furnace every month, when what your home actually needs is a battery charged once by a 2-hour fire. The equation behind it is simple. Q quarters meters, C delta T. Heat stored equals mass times specific heat capacity times temperature change. So, let's run those numbers. A Kachelofen weighs 500 kilograms, about $100 lb of solid masonry and ceramic tile. You burn a fire inside it for 2 hours, and the internal temperature reaches 600 degrees C. That's about 100 degrees F. Mass is 500 kilograms. Specific heat is 0.9. Temperature change from room temperature at 20 degrees C up to 600 degrees is 580. 0.9 multiplied by 580, $261,000 kJ of stored thermal energy. To put that in terms you can feel, that's the same amount of heat as a 4,000 W electric space heater running for 18 hours straight. All of it stored inside a stack of masonry bricks and clay, charged by one single fire that burns for 2 hours and then goes out. Now, compare that to your gas furnace. It runs a heat cycle every 15 to 20 minutes all night, burning fuel continuously to compensate for the heat it can't store. The average American household burns 3 to 4 therms of natural gas overnight during winter. At current rates, that's $3 to $5 per night, every single night, for 5 months of winter. The thermal battery's fuel cost for the same night is 15 kilo of dry wood, about 33 orilborn. In most parts of the country, that wood is free from fallen branches, construction scraps, or wood pallets that nobody wants. Now, you're probably thinking, if masonry is that much better, why doesn't anyone build heaters this way anymore? The answer has nothing to do with physics, and everything to do with what happens when a product works so well that people never need to buy anything again. Quick question for you. Which material stores more heat per kilogram for the same temperature increase? Option A, steel. B, clay brick. C, cast iron. D, copper. Now, take 10 seconds to answer the quiz below. If you answered B, clay brick, your instincts are exactly right. Clay brick's specific heat capacity is nearly double that of steel, which is the entire reason 800 years of Scandinavian winters were survivable with a single kakelugn heating a stone farmhouse through the night. The burn and release cycle is the third element, and this is where the kakelugn breaks every rule modern wood stove companies have taught you. Slow, low-temperature burning is the worst thing you can do with wood, and it's exactly what modern wood stoves are engineered to encourage. The kakelugn's combustion chamber runs at 800 to 900 grados C, about 1500 to 1600 Fahrenheit, for 2 to 3 hours, and that's the entire fuel input for the whole day. Burning hot and fast is more efficient because complete combustion at high temperatures extracts maximum energy per kilogram of wood and produces zero creosote buildup. Below 500 Celsius, wood gases don't fully combust. You're sending unburned energy up the flue as particulates and wasted heat. Incomplete combustion at low temperatures throws away 30 to 40% of available thermal energy. Most modern wood stoves are designed for smoldering, slow burns to keep a fire going all day. That approach is thermodynamically backwards, and it's also what causes dangerous creosote deposits inside your chimney. The kakelugnsofen does the opposite. Burn intensely for 2 hours, extract every joule of energy the wood can give, then stop entirely. The masonry combustion chamber itself amplifies efficiency because the thick refractory brick lining holds extreme heat during the burn, preventing the temperature drops that cause incomplete combustion. Now, here's where it gets interesting. After the fire goes out, the kakelugnsofen surface holds at 80 Celsius, about 176 Fahrenheit, for the first hour. By hour 6, it's still at 60 Celsius, 140 Fahrenheit. At hour 12, 45 Celsius, 113 Fahrenheit. And at hour 18, the surface still reads 35 Celsius, 95 Fahrenheit. That's meaningful, usable radiant heat for 18 consecutive hours from one afternoon fire. That's the burn and release cycle, and it's physically superior to anything running on your utility bill right now. But knowing the cycle is only half the picture, because the way that stored heat actually reaches your body isn't through the air at all. That's where something called the radiation wall changes everything, and it's why Scandinavians felt warm in rooms that a modern thermometer would call cold. The radiation wall is the fourth point. Forced air heating isn't heating your body, it's heating your ceiling, and the physics says it always will. There are two completely different ways heat travels from a source to your skin. Convection heats air, which then heats surfaces. Radiation emits infrared energy directly from a warm surface to whatever it hits. No air needed in between. Your forced air furnace uses convection. It blows warm air into the room, but warm air rises immediately to the ceiling. The floor temperature in a forced air-heated room is typically 8 to 12 Celsius colder than the ceiling. That's 15 to 22 Fahrenheit of difference. Your thermostat sits at mid-wall height, splitting the difference, and calls the room warm while your feet are freezing, and the top 3 ft of air near the ceiling are overheated and wasted. The radiation wall works completely differently. The warm ceramic tile surface of a Kachelofen emits infrared radiation in straight lines. That energy travels across the room and gets absorbed directly by whatever it hits. Your furniture, your walls, your floors, and your skin. The air in between is essentially bypassed. The Stefan Boltzmann law says radiant energy output scales with the fourth power of surface temperature. So, even a surface at 50 Celsius, about 122 Fahrenheit, emits persistent, meaningful radiant energy across an entire room. The measurable result from studies of traditional masonry stove heating is that people report thermal comfort at air temperatures 3 to 4 Celsius lower, about 5 to 7 Fahrenheit lower, than rooms heated by forced air. That isn't a subjective preference. It's because radiant heat warms the thermal mass of the room itself, the walls, floors, and furniture, which then re-radiate back to your body from all directions at once. That sounds completely backwards. A room that's 3 degrees cooler on the thermometer somehow feels warmer. Here's exactly how the physics makes that possible. Your thermometer measures air temperature. The radiation wall doesn't care about the air. It's heating you directly the same way the sun heats your face on a cold winter day, even when the air around you is below freezing. The cost reality is the fifth factor. The modern heating industry has built an entire business model on convincing you that staying warm costs thousands of dollars. The math doesn't support it. Materials to build a functional small-room masonry heater include 50 standard clay bricks at 40 cents each. That's $20, and 1 bag of fire clay mortar at $10. Total cost $30 to $40. Every tool you need is already in your garage. A professional full-size kakelung with traditional ceramic tiles installed in Scandinavia today runs $2,000 to $5,000. That still beats the total winter fuel cost of a gas furnace in 3 to 4 years. Compare that to a modern pellet stove at $2,000 to $3,000 plus $200 to $400 per winter in pellet fuel plus electrical power to run the auger, the fan, and the controls. The kakelung burns any dry wood, including construction scraps, fallen branches, and wood pallets. Historical Swedish farmhouse data shows 2 to 3 cords of firewood per winter heated a full family stone farmhouse with a properly built kakelung. The modern equivalent in natural gas runs $1,200 to $2,000 per winter. Your per-hour breakdown on the kakelung is this. 15 kilos of dry wood costs $0 to $3 depending on your source, provides 18 hours of heat. That's 17 cents per hour at most. Electric baseboard heating at current U.S. average rates cost 15 to 35 cents per hour and requires that electricity running the entire time. Find fire clay mortar at any hardware store. Don't buy it on Amazon. The markup is criminal. An infrared thermometer gun, about $15 to $20, is useful for verifying your stove's surface temperature at each hour of the release cycle. The $40 version works. It's always worked. And the only thing that changed is who profits from your heating bill. The industry burial is the final point. The Kachelofen wasn't replaced because something better came along. It was replaced because it made utility companies obsolete. This wasn't a fringe technology. The Kachelofen was standard residential heating across Sweden, Finland, Germany, Russia, and Eastern Europe from the 12th century through the 1940s. It was the standard, not some alternative fringe method, not a primitive workaround, the actual default way people heated their homes. After World War II, Nordic and Western European governments, backed by utility infrastructure investment, subsidized electrical grid connections and electric heating equipment through the 1950s and 60s. The grid was being built, and it needed customers. Electric heating companies ran campaigns calling Kakaloven primitive, fire hazards, and inefficient. None of those claims had engineering data behind them. The Kachelofen's combustion efficiency at 90% outperformed the early electric resistance heaters in total energy utilization. But efficiency wasn't the point. The point was recurring revenue. A masonry stove heated by firewood from a backyard produces no monthly bill for anyone. By 1970, new Kachelofen installations had dropped over 90% across Scandinavia, not because they stopped working, but because the energy grid needed recurring customers, and a thermal battery that runs on free wood doesn't create any. The pattern is always the same. The $2 powder that beats a $3,000 AC unit. The sand filter that purifies water forever. The thermal mass shelter that hides from drones. The physics never changes, but the industry always does. Turns out, the Kacheloven revival is already happening. Off-grid homesteaders and energy-independent households across Scandinavia and North America are building them again. Sweden now has certified Kacheloven installers who can't keep up with demand. The internet broke the information barrier. The physics was always there, waiting. One more question. How many hours can a properly built masonry kakaloon radiate usable heat from a single 2-hour fire? A. 4 hours. B. 8 hours. C. 18 hours. D. 36 hours. Take 10 seconds to answer the quiz below. If you answered C, 18 hours, congrats. You now understand thermal mass physics better than most HVAC engineers. The math is real, and it doesn't bend. 500 kilon of masonry at 600 Celsius. That's 261,000 kilojoules of stored energy, released at 40 to 80 Celsius surface temperature, doing exactly what physics says it should do. The industry didn't bury the kakaloon because it failed. They buried it because it worked too well. Now you know why a $40 masonry structure outperforms a $3,000 furnace on pure thermodynamics. But there's actually a second material sitting on hardware store shelves right now that stores heat with even greater efficiency than clay per kilogram, and it costs $3 a bag. That's exactly what the next video covers. If this story changed the way you look at the simple materials in your backyard, please subscribe and like the channel. We are unearthing the history they tried to bury. Build your own future. The next treasure of knowledge will be opened soon.